Hi, my name is Eric Wilson. I'm a senior research engineer at the National Renewable Energy Laboratory. Today I'm going to be talking about bottom-up demand modeling. To introduce the concept of bottom-up demand modeling, I first want to talk about how grid planners today typically assume constant demand profiles when projecting out into the future, or they may use top-down econometric models to scale the demand profile into the future. This means that future years will have the exact same hour-to-hour electricity demand as the historical year being projected forward. However, many grid planners, electric utilities, and government regulators are now realizing that the emerging importance of being able to predict the impact that different technologies or policies might have on hourly electricity demand profiles. Swan and Ugersol in 2009 published a taxonomy of models that could be used for forecasting residential energy consumption. This provides a nice framework for understanding where bottom-up engineering demand models fit within the context of all types of building stock or building demand modeling. The tools I'm going to be talking about today, ResStock and CompStock, which have been developed by NREL for the US Department of Energy, fall on the bottom-up engineering model side and incorporate aspects of the population distribution archetype and sample model types that were categorized by Swan and Ugersol. For today's talk, I'm going to use our work for the City of Los Angeles on their 100% renewable energy study as a case study to explain how bottom-up demand modeling can be used. Our application of ResStock and CompStock for building sector load modeling for the City of Los Angeles was a first of its kind analysis. And the analysis sought to understand what role the building sector plays in achieving 100% renewable energy for a city and a utility company, and projected different levels of growth in the building stock, electrification of space heating and water heating, different efficiency levels, and demand flexibility projected out to the year 2050. And then the results from the building sector modeling were passed to other models used for the study to understand what the impact of these different scenarios would have on necessary grid infrastructure upgrades, new generation capacity, etc. So the goals for today are, one, to become familiar with the methodology that we use for building sector load modeling, review load projection scenarios, and then review some sample results. For the purposes of today's presentation, we define the building sector to mean residential buildings and commercial buildings. The models that we're using currently don't include distributed solar PV, electric vehicle charging, demand response, or industry or other special loads. These are handled in other parts of the model for the Los Angeles case study. So building stock simulation can kind of be thought of if you're building a city out of Lego bricks and you want to represent the city. It's not quite that you would build one model building for every one building in real life, but it's actually not too far away from that. We typically use on the order of one building simulation model to represent 200 buildings in real life. So it is quite a high granularity model. So a little bit of background on the ResStock and Comstock tools. These tools bring together three key components that enable us to get a really high granularity look of residential and commercial building stocks. So one, they include a detailed database of building stock characteristics that we've compiled from dozens of different data sources for the United States. And two, they use physics-based computer modeling, so we can look at what-if scenarios about different technologies or policies being deployed through the building stock. And finally, because of the large scale of the simulations, we have to make use of high-performance computing, either the supercomputer that we have at NREL or cloud computing resources. So first, the building stock characteristics database. This includes a variety of data sources that we've compiled together and structured in a tree of conditional probability distributions in order to represent the diversity of characteristics that exist within the existing building stock. So on the residential side, this includes diversity in terms of when homes were built, what areas of the country they were built in, different insulation levels that can be found within the buildings, different building types, single family and multifamily buildings, as well as different heating and cooling system types and different fuels used for space heating and water heating. Diversity across all of these different components, and in many cases there's correlations or joint probability distributions that define, for example, how insulation levels vary depending on what vintage the home was constructed in, or what location in the country it's located in. On the commercial building side, there's similar array of diversity across different building types, from offices to schools to retail, as well as hours of operation, HVAC system types, etc. For the work for the city of Los Angeles, we enhanced the national and regional data sources that were used for the national US versions of ResStock and Comstock, and supplemented those with about a dozen different data sources that are specific to the state of California or the city of Los Angeles. So this includes GIS data, a tax assessor database for Los Angeles, as well as various other data sources that provide much more granular and location-specific information that we can use in our modeling. So second, the physics-based computer modeling. For this work, we used the OpenStudio software development kit and the Energy Plus simulation engine for sub-hourly building energy simulation. This allows us to look at what-if scenarios about different technologies being deployed, even if those technologies don't exist in the stock today. And finally, for high-performance computing, for this analysis, we used the supercomputer at NREL, and we ran 75,000 simulations to represent the baseline residential and commercial building stocks. And then we did seven future year projections, stepping forward 5 years at a time out to the year 2050. And for each of those, 4 different load scenarios. So in total, we ran over 2 million simulations. If you were to try to run that on a laptop, it would take 20 years. So the supercomputer was definitely necessary. And we run orders of magnitude more simulations when we do national scale studies compared to the city scale analysis. So why this number of simulations? Well, we've done a lot of work characterizing the number of simulations that's necessary to represent the diversity of the building stock. And it really depends on what questions you're trying to answer. But you can put models on a spectrum from low granularity to high granularity, where on the low granularity side, maybe you're modeling a handful of prototype buildings. High granularity, you're trying to model every single building. Most of the time, you don't have the necessary data to model every single building with accuracy. So we fall in the middle, where we're running hundreds of thousands or up to 1 million representative building models for ResStock and Comstock, and seek to represent the diversity of characteristics in the stock without having to model every single building. And we've done some work looking at if you have a probability distribution for an input, say the number of floors in a building, and that's defined as a function of building type, the year which the building was built, and the floor area. You can see how the number of samples necessary to have the distribution of this characteristic in your samples match the input probability distribution that you fed into your sampling algorithm. So in this case, we can see that with 10 samples, it does a very poor job of matching. With 100, does a little bit better. Each of these dots or circles represents one combination of characteristics. With 1,000 samples, it does a bit better. 10,000 does a bit better. And then with 100,000, you can see that it's mostly lining up on this y equals x line here. So that's just a sample of some of the work we've done to study how many samples are necessary to represent the diversity in the building stock. You can also do a similar exercise looking at how the output from your models, whether that's energy savings or peak demand or other quantities of interest, converge as you add more and more samples. So next I'm going to talk a little bit more about how we projected out different scenarios into the future. So first, our design philosophy for these scenarios was that we looked at a range of different outcomes, and we weren't defining specifically what technologies or policies would achieve those outcomes, but instead we defined the outcomes in terms of a certain level of efficiency or a certain level of electrification, and then backcast what rates of adoption would be necessary to achieve those market saturations. So in other words, we weren't trying to model or project likely rates of adoption of different technologies, but rather we were saying if the rate of adoption is X, then here is the outcome in terms of demand profiles. There are different approaches to this, and certainly you could use an approach to try to model adoption of technologies based on payback periods, etc. But that's not what was done for this particular analysis. So to summarize, the building sector, for the building sector, we looked at 4 different scenarios. One was a reference level of energy efficiency and electrification. Second was a moderate level of energy efficiency and electrification. Third, we did a high efficiency and electrification, basically the maximum level of electrification and energy efficiency that we thought was possible. And then we also looked at a stress scenario designed to stress the electric grid, where we use the maximum or high level of electrification, but used to reference the lowest level of energy efficiency to understand the impacts that would have on the electric grid. All of the projections we did use the same building stock growth rate, though certainly that's something that could be varied. And then all the projections use the same weather. And for this analysis, weather from the year 2012 was chosen for both the building sector modeling and the grid or power sector modeling. But certainly you could project changes in weather into the future and try to understand what effect that would have on the demand profiles. Okay, so first touching on the building stock growth projection. So we used projections from the California Department of Finance and modeled out demolitions and new construction of residential sector by vintage and building type. So multifamily versus single family. And then we had a certain level of demolition of older buildings and projected new buildings in each decade. On the commercial building side, similarly, we used a different data source for the projections, but projected out new vintages coming into play, and also growth for different building types. And in this case, the largest growth was projected in education, hotels, healthcare, and other building types. So electrification was one of the parameters that we varied. So just to give one example here, for three different scenarios, we had a reference level of electrification of residential water heaters. So currently the installed stock has about, say, 5% electric water heaters, with the rest being using natural gas as a fuel. And you can see that we increase that over time for the moderate and high scenarios, so that by 2045, in the high electrification scenario, you see 100% electric water heating. And to achieve that level, you can see that we backcast what the sales, what the percentage sales would have to be. So in order, using standard lifetimes turnover rates for residential water heaters, in order to get to 100% electrification by 2045, you need to have 100% sales of water heaters be electric by the year 2030. Of course, there's different ways to achieve that. You could model early retirement and adoption as a way to achieve the same end goal. But in summary, this is what we modeled, and this was done for all end uses where natural gas was used. Okay. And then, so for energy efficiency adoption, we similarly modeled 3 different scenarios, looking at changes to the equipment stock. So this example shows residential air conditioning, and how we have, in the reference case, over time, fewer households with no air conditioning, and an increasing fraction of households that have central air conditioning, central ducted air conditioning. And then about constant saturation of room or window air conditioning units. And then you can see the different shades of colors here are different efficiency levels of air conditioners. And in the moderate and high scenarios, you can see that the higher efficiency pieces of equipment make up a larger portion of the installed stock. You can also see in the high scenario, especially, the fraction of homes with no air conditioning decreased substantially, and that's related to the increase in heat pumps as part of the high electrification scenario. So similarly, this was done for all pieces of equipment and other characteristics like insulation, and both for all residential building types and all commercial building types. These types of projections were made mostly based on our domain knowledge and experience with building codes, etc. Okay, so now to touch on some sample results. What do the results look like? So this shows an example week in the month of February from one of our runs. And you can see that we can plot the electricity demand profiles broken up by different end uses. So we know how much of that profile was due to cooling, heating, water heating, etc. So this is just showing the residential sector load. You can see that the first 2 days of this week were much hotter than the rest of the days. So there was more energy used for cooling. And we superimposed the outdoor temperature from the 3 weather stations that were used for this analysis. There are many other ways to present this information, looking at peak days. You can plot all 8760 hours of a year. Okay, so one point I wanted to touch on here is that when we did the first run of the baseline current year building stock, we compared the results of our models to some ground truth data that we had from the utility company, and we found that they didn't agree. That's not very surprising for anybody who's done building energy modeling. You know that it takes some work to calibrate models to reality. So that's what we did. And after this calibration process, you can see that the monthly totals of electricity consumption compared well to our model output. Those daily totals using the same weather compared well. And then you can also look at hourly results, and you can see that there are some differences, but in large part, the model agreed with the ground truth data that we had. So how did we do this? Well, the data sources we had access to, it depends on what kind of data you have access to, but in this case, we had access to monthly billing data for all customers of this utility. We also had access to their load research data, which was from a sample of their customers, both in the residential and commercial sectors. So that was hourly data as opposed to monthly. But it was for the sector total. It didn't show us the diversity in behavior there. And then finally, we also had access to their smart meter or advanced metering infrastructure data, which has 15-minute resolution, but only for a subset of the customers, especially on the commercial building side. That was useful for comparing results for specific building types. And finally, I wanted to show some example results from the scenarios. So we can look at peak winter day profile for the residential and commercial sectors. And so this is at 24 hours for the average winter day, average winter peak day for the 4 different scenarios: reference, moderate, high, and stress in the year 2045. So you can see, you can look at the difference between, for example, high and stress, and see that the fact that high had a high level of energy efficiency and high level of electrification, but stress had a low level of energy efficiency and a high level of electrification. There was about a 10% difference between those 2 scenarios on this particular day. And then similarly, you can look at an average winter day when there's a lot less difference between the scenarios. Again, this is just one way of looking at the results. The most valuable outcomes were to take the full 8760 results and feed them into the capacity expansion models and the bulk power dispatch models to understand what implications there were for the grid, both in terms of generation and dispatch day to day. So with that, just wanted to conclude and say that through this presentation, I've explained that you can look at different levels of growth in the building stock, different levels of energy efficiency, electrification, air conditioning, demand response, and that these will have significant impacts on your building sector electricity demand profiles. And I've shown how bottom-up engineering models can be used to evaluate the building sector electricity demand with a really high level of granularity to understand how the diversity of the building stock responds to these different scenarios, and how that can therefore inform decisions made both about building sector decision policies, technologies, as well as on the power sector side. Thank you for listening, and that concludes this presentation.